Hello students, this is Dr. Sansem. I want to do a short video for you with an example of an equilibrium problem where we're using a rice table to solve for equilibrium concentrations. So in this instance, we've got this gas phase reaction where hydrogen and iodine gases react to form hydrogen iodide gas. And our initial conditions are that we have 2 atmospheres of hydrogen and 3 atmospheres of iodine. We have 0 atmospheres of HI. And the temperature is 448 degrees Celsius, and K at 448 is 50.5. So the first thing that I'm going to do is ask myself, which direction is this reaction going to go? So I'm going to calculate Q for my initial conditions. The pressure of HI squared divided by the pressure of H2 times the pressure of I2. And I have no atmospheres of HI at the beginning, so that's 0. And then I'll have 2 times 3, and in the end, my Q is actually 0. Since my Q is 0, Q is less than K, and that means my reaction will proceed in the forward direction. Okay, well that's sort of what I expected because I'm starting out with all reactants, so it makes sense that I would have to make products in order to reach equilibrium. And what I'm going to do now is set up a rice table where I have my reaction, H2 plus I2 makes 2HI. And I have my initial pressures. For hydrogen, it's 2 atmospheres. Iodine is 3 atmospheres. HI is 0. I'm going to have some change, and then I'm going to reach equilibrium. So in this case, because I know the reaction is going in the forward direction, I'll lose some amount X of hydrogen and the same amount X of iodine because they're in a 1-to-1 stoichiometric ratio. But my HI, I'm going to gain twice as much. So I'll have 2X for my HI. And I'll add together my initial and my change to get my equilibrium concentrations. 2 minus X, 3 minus X, and 2X. Now we know that our K is 50.5, so we can substitute these things in. We should have our pressure of HI squared, which will be our 2X squared, and then hydrogen times iodine on the bottom. Unfortunately, our K is not small, so we're not going to be able to use an approximation. I'll just multiply this out and get 4x squared on the top, and then 6 minus 5x plus x squared on the bottom, and that equals 50.5. So I can rearrange this into an ABC format for the quadratic equation. Can rearrange this into an ABC format, and I end up with 0 equals 46.5 x squared minus 252.5x plus 303. And I can use this for my A, B, and C values in the quadratic equation. So I'll get x equals negative 252.5 plus or minus the square root of negative 252.5 squared minus 4 times 46.5 times 303, all divided by 2 times 46.5. When I solve these out, I'll get 2 values for x. It will be either 3.64 or 1.79. So now I have to look back at my rice table and I have to ask myself which one of these makes sense. Well, the value that's 3.64 isn't going to work because if I subtract 3.64 from 2, I actually end up with a negative concentration, and I'm not allowed to do that. So I'm going to choose 1.79 as the x that I'm going to solve for. So then the last step is that I'm going to solve for those equilibrium concentrations, or rather pressures. So the pressure of H2 should be 2 minus 1.79, which gives me 0.21 atmospheres. My pressure of I2 is going to be 3 minus 1.79. That gives me 1.21 atmospheres. And my pressure of HI is going to be 2 times 1.79, which is 3.58 atmospheres. The last thing I'm going to do is just a double check to make sure that when I plug in these equilibrium concentrations into my K expression, I do get the same value for K that I started out with, or something very close to it. So I'm going to take my HI squared divided by my hydrogen times my iodine, and when I multiply that out, I get 50.4, which is close to 50.5, which is what I started with, so I'm going to say that checks out. So in this problem, we had initial concentrations. We used our Rice table to identify what our equilibrium concentrations were going to be. And then we plugged those into our K expression to solve for x. We had to use the quadratic equation here because 50.5 was a pretty big K value, and so we couldn't assume that the change would be small, and that was justified considering that our x value is 1.79, which is pretty big compared to 2 or 3. That's about the same size, so not small compared to those. We use the quadratic equation. Only one of the answers makes sense, and this is usually the case when you use the quadratic equation. One of your answers is going to end you up with a negative concentration, which isn't possible in reality, so you know that that's incorrect. And then we substituted back in for our value to get our equilibrium concentrations. And the last thing we did was just check to make sure that we get something that's similar to what we expect when we plug those equilibrium concentrations or pressures back into our equilibrium expression. We should get something that equals the equilibrium constant. Okay, that's it. I hope that's helpful.